It is a great honor and pleasure to receive the Lagrange Award in recognition of my contributions to nonlinear physics. I'd like to express my deep gratitude to those involved in the selection process for their efforts and also extend my sincere thanks to all who have supported me up to this day. Over the past half century, we have witnessed significant advancement of the science of coupled oscillators. In this talk, I'd like to briefly describe a modest contribution I could make in the early stage of this field and how it subsequently helped shape its development. Let me begin by sharing a bit of my personal experience going back to half a century ago when nonlinear dynamics was still in its early phase and the people working in this field was still few. It was about that time that I changed my research field from the statistical physics of thermodynamic phase transition to the physics of self-organization phenomena in far from thermal equilibrium. There were at least two reasons for this change. One was the appearance of Kenneth Wilson's renormalization group theory of the second-order phase transition, which finally settled the long-standing problem of how to deal with critical fluctuations. Since his theory was so epoch-making that I thought that I could no longer make any significant contribution to this problem and gave up to keep staying in the same field. The other reason was that I came across Glassdorf-Prigodin's book entitled Thermodynamic Theory of Structure, Stability, and Fluctuations, which had been published a few years before. This book gave me a strong impact and encouraged me to step into a new field which was still uncultivated, but potentially going to form a rich field of science. Among a variety of self-organization phenomena, I was particularly interested in the dynamics of coupled oscillators. And this research theme later came to occupy the central place in all my research career. Although it is not widely cited, the work which represents an important starting point for me is a short paper written with Toshio Suzuki in 1974, where we derived perturbatively an equation known as the complex Ginzburg-Landau equation from a certain reaction diffusion model. Indeed, most of my subsequent works of relative importance were rooted in this short paper. Among others, I will select out the following three works. The first is a derivation of what people call the Kuramoto-Swasinski equation. And the second work, which I will discuss at some length later, is a proposal of a mathematical model called the Kuramoto model. And the last one is a theoretical finding of a curious pattern of synchronization, which was the first example of the so-called chimera states. Looking back now, I realize that all these works resulted directly or indirectly from the complex Ginzburg-Landau equation or its variant through a reduction method called the phase reduction. This is a method of approximately describing coupled limb cycle oscillations only with phase variables. Incidentally, I hesitate to refer to my own name frequently in this talk, but please understand that this is something unavoidable. Now, I am going into some details of these works one by one, but before that, let me describe briefly how the work of deriving the complex Ginzburg-Landau equation came out. One thing which was important to me was that I learned about an oscillatory reaction diffusion model called the Brasslator and the glanced of previous book. Another source of my motivation of this work was the self-organized wave patterns of the oscillatory Belousov-Jabotinsky reaction, which was attracting widespread attention in those days. I wished to understand the wave patterns of the Belousov-Jabotinsky reaction in terms of the Brasslator. An idea which came up to me was to focus on the situation close to the onset of oscillation, that is a Hopf bifurcation of the Brasslator. Although I didn't even know the term Hopf bifurcation at that time, I thought that this model equation would then become much simpler and might lead to a qualitative understanding of the observed wave patterns. Fortunately, this idea was given shape with the help of the perturbative method of Newell and Whitehead. They had developed this method for deriving a small amplitude equation near the onset of the Rayleigh-Benner convection. We successfully reduced the Brasslator to the complex Ginzburg-Landau equation, where W is a complex field with real amplitude R and phase theta. Since I will frequently refer to this equation, let me hereafter call it simply CGL. Of course, the same equation can be derived also from a much more general class, general reaction diffusion equations by reduction. And this type of reduction method is generally called the center manifold reduction. We submitted the short paper on this work to Physics Letters A. The paper was entitled Reductive Perturbation Approach to Chemical Instabilities. The term reductive perturbation was borrowed from the same term used for the derivation of soliton equations from a certain class of wave equations. Unfortunately, our paper was rejected for the reason that its content was not appropriate for physics journal. Unlike today, the concept of statistical physics was quite limited in those days, so the reason for the rejection is understandable. Fortunately, after resubmitting it to another journal, it was accepted immediately. Let me now proceed to the partial differential equation called the Kuramoto-Shibasinsky equation, and hereafter I will simply call it the chaos equation. This equation was derived in 1976 as a phase reduction of CGL. As is well known, CGL admits a family of plane wave solutions over the whole range of wavelengths. Each plane wave has its own frequency. This fact implies that self-oscillating fields are dynamically flexible in the sense that they can control their frequency arbitrarily by creating a plane wave of suitable wavelengths, and in that way adapt to an external or internal frequency sources. Because of this flexibility, plane waves, possibly with some distortion, constitute building blocks of the wave patterns such as expanding concentric waves and rotating spirals. Such is a commonly known fact today, but in those days I was ignorant of it and mistakenly expected that something like the Turing instability, the wave patterns of the Belousov-Jabotinsky reaction would arise from an instability of spatially uniform oscillation. So I studied its stability. In terms of this rescaled CGL, the instability occurs for a negative value of 1 plus C1, C2. This is called the Benjamin Fair instability, and this instability condition itself had already been known by Lange and Newell 2 years before my derivation of the chaos equation. But there had been no argument about what would happen after the instability. Contrary to what I had expected, what happened was spatial-temporal chaos and not a regular wave pattern. But this misconception fortunately led to the discovery of the chaos equation. How to derive the chaos equation from CGL is the following. We impose the hypothesis that the modulus R is given by a function of the phase theta, or a function of various space derivatives of phase. Then we make an expansion of R in powers of all its arguments and substitute this expansion form into CGL. The resulting CGL determines the expansion coefficient and at the same time gives an evolution equation for the phase in terms of its various space derivatives. And out of these space derivatives, we single out the most dominant terms, assuming that the instability is sufficiently weak. The resulting equation is a chaos equation. After rescaling, the equation becomes parameter-free. Numerical simulation of this equation for sufficiently large one-dimensional system revealed that the solution behaved chaotically in space and time. Such behavior is called the phase turbulence. Next year, Szybaczynski found the same equation independently as an equation describing weakly unstable flame front of combustion. Chaos-like equations also appear in other physical contexts, such as viscous liquid flowing down on a vertical wall, epitaxial growth of solid surface by sputtering, and the instability of trapped ion mode in tokamak plasmas. When we derived the chaos equation, that is mid-1970s, the science of chaotic dynamical systems was undergoing a remarkable development. Many theorists studied ordinary differential equations and discrete maps exhibiting low-dimensional chaos. On the other hand, the phase turbulence we found was a chaotic solution of a partial differential equation and not ordinary differential equation. Therefore, it was natural that some mathematical scientists raised the following question. Are ordinary differential equation chaos and partial differential equation chaos equivalent? This was answered affirmatively, at least for the one-dimensional chaos equation with finite system length, because the existence of the so-called inertial manifold was proved there. Inertial manifold refers to a finite-dimensional, globally attracting manifold in which all infinite-time solutions come to be included. Thus, the long-time behavior of the system becomes mathematically equivalent to ODE dynamics, and this directly leads to the equivalence between ODE chaos and PDE chaos. From physics side, another issue was raised. This was how a coherent structure is transformed to turbulence through successive bifurcations. Indeed, the scenario leading to turbulence had been one major issue of fluid dynamics since Landau's speculation that developed turbulence could be represented by a high-dimensional torus. But the case of the Rayleigh-Benner convection at least contradicted this classical picture, because the existence of low-dimensional chaotic attractor was confirmed there. Still, how this attractor changes to develop turbulence remained unclear. In order to gain some insight into this problem, the chaos equation attracted attention as the simplest analog to the Navier-Stokes equation. Fortunately, the parameter-free one-dimensional chaos equation includes only one control parameter, which is a system length L, something similar to the aspect ratio of the Rayleigh-Bénard convection. Although it was natural to expect, extensive numerical study of the chaos equation revealed the process of successive appearance of higher and higher dimensional chaotic attractors with increasing L, eventually leading to a spatial-temporal chaos of extremely large degrees of freedom. Besides the two topics on the chaos equation just described, this equation has been discussed in relation to many other problems. It seems that all these works have made use of its simplicity as a minimal partial differential equation displaying spatial-temporal chaos. But if viewed from another angle, the chaos equation represents a concise mathematical manifestation of the fact that locally coupled fields of oscillators can easily display turbulence. It seems that this fact hadn't clearly been recognized before the appearance of the chaos equation. After that, however, numerous works appeared on the various forms of turbulent behavior of CZL, such as amplitude turbulence, spiral wave turbulence, and spatial-temporal intermittency. Let me now turn to my next work, the so-called Kuramoto model, and first tell you how this model came into being. The beginning was that I was inspired by Art Winfrey's paper of 1967 entitled Biological Rhythms and the Behavior of Population of Coupled Oscillators. Since I was not so familiar with mathematical biology, it was not until 7 years after the publication of Winfrey's paper that I finally came across it. I was already in my mid-30s while Winfrey wrote his paper in his mid-20s. The impact of Winfrey's paper was great. First of all, he described coupled oscillators only with phase variables and successfully worked out a simple mathematical model for infinitely large assemblies of coupled oscillators. At that time, this was a radical new approach, although it is now commonly known that the phase description of coupled oscillators is justified when the mutual coupling is sufficiently weak. Based on this phase oscillator model, he claimed, under the assumption of global coupling, the existence of a critical condition for the onset of collective oscillation. Here, the system components are dynamically active units and not inactive elements such as atoms and spins. And such a new type of phase transition was a fresh surprise to me. However, Winfrey's argument on the existence of phase turbulence was not convincing enough, so I wished to simplify his model to make it analytically tractable, but preserving the original form as much as possible. What must have to be simplified was his coupling term, which was given by a product of two functions representing influence and simple sensitivity. I recalled my preceding work on CGL and noticed that if CGL was spatially discretized, the phase reduction of the effective coupling, the diffusive coupling, was given by a simple trigonometric function depending only on the phase difference. Even a cosine component didn't appear with a suitable choice of the parameters of the original CGL. Following Winfrey, I assumed that the system size is infinitely large. and the distribution of the natural frequencies is given by a unimodal symmetric function. The model obtained in this way is commonly called the Kuramoto model. I thought that thanks to the global coupling and sinusoidal coupling function, this model could be handled analytically by applying the elementary idea of the mean field theory of thermodynamic phase transition. Indeed, this was accomplished by introducing an order parameter, which is a quantity analogous to total magnetization in magnetic phase transition. But in the present case, its amplitude gives a measure of the strength of macroscopic oscillation. Although I was faced with some non-trivial problems coming from the deterministic origin of randomness, they were cleared, and by imposing certain hypotheses, a self-consistency equation for the order parameter was obtained. Its solution clearly showed the existence of a critical coupling strength above which a solution of collective oscillation bifurcated from the constant solution, a constant non-oscillatory solution. I took it as a matter of fact that, like thermodynamic phase transitions, an exchange of stability occurred between these solutions across the critical point. But I couldn't show any evidence to support this belief. In fact, this stability problem was challenging and became one major issue in later years, as I will touch upon shortly. Incidentally, 11 years later, that is in 1986, a slightly generalized solvable model was proposed by Sakaguchi and myself by including a phase lag and a coupling function, which is equivalent to including a cosine component. This model is commonly called the Sakaguchi-Kuramoto model. The effect of phase lag is crucial to the undamped propagation of phase waves when the coupling becomes local. In any case, when I completed this work, I never imagined that this model would later come to be called by my own name and became relevant to such a wide range of fields. So I didn't even write a regular paper, but instead presented a short talk on this model at a certain international symposium held in Kyoto and submit a short report for the proceedings. Naturally, this report, which was just over 2 pages long, remained unnoticed for the subsequent several years. Probably the first person who discovered it was none other than Winfrey himself. I received a short, handwritten letter from him, and to my delight, there were a few words of praise for my model. In the same letter, he asked a sharp question about the stability of the macroscopic states obtained, and naturally, I had no answer. So let me come back to the stability problem of the collective states. Indeed, their stability was not obvious at all because, unlike thermodynamic phase transition, our transition has no potential to be minimized, and it's also quite different in nature from the conventional bifurcation of dynamical systems. What was embarrassing about this problem was that when we try to examine the stability of the incoherent branch of the solution using the standard method, we are faced with a spectrum distributed continuously on the imaginary axis. Formally, this implies the neutral stability of the incoherent state, but this seemed contradictory to the asymptotic stability of the corresponding macroscopic state, which was confirmed by numerical simulation. This seeming contradiction aroused considerable mathematical curiosity. The clue to the solution was to correctly formulate the phase mixing mechanism similar to that of the random damping of collisionless plasmas. A number of theories challenged this problem, including Strogatz, Mirolo, and Crawford, and this issue, including the post-critical dynamics, was settled by the end of the last century. But 15 years or so later, even more rigorous mathematical theory was formulated by Hayato Chiba. Aside from such stability issue, the research on the dynamics of coupled oscillators has been given a fresh momentum since the beginning of this century. The most widely studied oscillator model there was sinusoidally coupled phase oscillators. It seems that there were at least two factors which promoted such new development of this research field. One is a theory of Edward Ott and Thomas Antonsen, which appeared in 2008, and the other is the appearance of mathematical models of complex networks. Ott-Antonsen theory deals with large assemblies of sinusoidally and globally coupled phase oscillators with randomly distributed natural frequencies. Their theory is remarkable in that it succeeded in drastic reduction of the high-dimensional dynamics of large assembly to its macroscopic dynamics of extremely low dimension. In particular, when the frequency distribution satisfies a certain condition, an evolution equation for the order parameter can be obtained in a closed form. Their theory broadened largely the class of problems that can be handled analytically. The sudden growth of the field of complex networks also expanded largely the scope of the dynamics of coupled oscillators. Around the turn of the century, two mathematical models of complex network were proposed in succession. They are the small world network of Watson-Strogatz, and the other is a scale-free network of Barabasi and Albert. But for a long time before the new development of the network science, most studies of large systems of coupled oscillators had been limited to the regular connection topology classified only according to the coupling range, like global coupling, local coupling, and their intermediate. However, the sudden upsurge of the field of complex networks drastically changed the situation. The key issue there was the relation between the network topology and the dynamics. A large number of studies emerged on this issue. They include the study of how the synchronizability changes as the small worldness of the network is changed. And as for the scale-free network, how the critical condition for the onset of global synchrony and the nature of collective oscillation depend on the degree distribution and the other network characteristics, such as how strongly the network is clustered. Ott-Antonsen's theory was also applicable as an approximate theory to some of such problems. Besides such generalizations from regular to complex topologies, the classical phase oscillator model with sinusoidal coupling has been generalized in various ways. A few of them are the following. A remarkable recent generalization is to introduce many-body interaction, or the so-called higher-order interaction, in place of the traditional pair interaction. And we look forward to seeing how research on this class of systems will develop in future. As a generalization of the coupling function, importance of time delay in some practical situations was suggested. The intrinsic dynamics of the individual oscillator was also generalized to include an inertial term, which has the effect of frequency adaptation. Another interesting generalization is to extend the phase to a multi-dimensional variable. These generalizations and many other generalizations were required from practical purposes. For instance, the effect of inertia was thought necessary for the application to power grid dynamics, and extending the phase to a multidimensional variable was intended for the application to such problems as opinion dynamics and the study of coordinated group behavior of animals, and also artificial neural networks. Through the study of such generalized phase oscillator models, it has become clear that synchronization phase transition is not always continuous, but this continuous transition or explosive synchronization occurs rather easily. Since this fact will likely have significant practical implication, we expect further investigation. In any case, the scope of the application of the phase oscillator models has expanded so widely that I can no longer grasp the whole picture. I will now move on to the issue of chimera states. A chimera state is generally understood as referring to a state where coherent and incoherent parts coexist in a system composed of identical oscillators coupled homogeneously. There seems to be a general consensus that the first example of chimera states was found in 2002 in my joint work with Dorje and Batoktok. This was when we were studying non-locally coupled oscillators. But preceding this work, going back 7 years or so, I had been turning my attention to non-locally coupled oscillators, expecting that some new type of dynamics might emerge. Non-local coupling also has practical significance, but I will omit that discussion here. Fortunately, my expectation was met. As a simple mathematical model, I considered a non-locally coupled CGL in one dimension with exponential coupling kernel. My first question was, what would happen if the Benjamin Fair instability occurred in this system, causing turbulence? As long as the instability remains sufficiently weak, the turbulent fluctuation would be limited to a region of wavelengths much longer than the coupling range. Then the non-local coupling would practically be the same as local coupling, and nothing interesting would happen. But how about if the turbulence became stronger and stronger, generating fluctuations with shorter and shorter wavelengths? In fact, the fluctuations eventually penetrated deep into the coupling range, as was confirmed numerically. Well within the coupling range, there is no more characteristic length scale. Consequently, the fluctuations occurred in such scale-free domain were expected to obey self-similar statistics, for instance, characterized by power law short-distance correlation. This was confirmed by numerical simulation, and its qualitative interpretation was also given. This was a joint work with Hiroya Nakao, a graduate student at the time, and also with Padok Tok, who joined us a little later. I also studied the phase reduction of the same model, but as long as turbulent fluctuations are concerned, I couldn't find any other interesting results. However, under non-turbulent condition, in contrast, something peculiar occurred, which later came to be called the chimera state. This was numerically numerically found by Buttock talk. The data he obtained showed that non-locally coupled systems split into two regions. In one region, the oscillators were completely synchronous, while in the other region, their phases were randomly scattered. The reason for this phase scattering is that their drift velocities were distributed, although they formed a systematic curve with a single hump. I saw that such coexistence pattern could be accounted for in the framework of the mean field theory. So I introduced the local order parameter, which is a space-dependent generalization of the global order parameter and is defined by a weighted local average over the coupling range instead of global average, imposing the hypothesis that the local order parameter itself is steadily oscillating. A functional self-consistency equation was obtained for this quantity. I found that other than a trivial solution representing global synchrony, this equation admitted the spatially non-uniform solution, and this solution corresponds to the coexistence of coherence and incoherence. The reason is easy to see from the mean field picture. Indeed, this picture says that the oscillators can be regarded as mutually independent, but they are only under the forcing from the mean field. This implies that there should be a critical amplitude in the mean field or the local order parameter, below which the individual oscillators are unable to synchronize the weak forcing of the mean field, implying incoherence, while above the critical amplitude, they can synchronize the strong forcing, implying coherence. In this way, the hybrid pattern of coherence and incoherence was consistently interpreted. Our theory attracted the attention of Abrams and Strogatz, and 2 years later they presented a more detailed analytical study of the same model as ours, except one point that our exponential coupling kernel was replaced with cosine kernel. In the same paper, they proposed the term chimeral states for such coexistent states of coherence and incoherence. The impact of this term was so strong that it contributed greatly to the subsequent development of the research area of complex patterns of synchronization. Abrams and Strogatz have also made other important works on chimeral states, but let me introduce here another work on our side. I thought that if a steadily rotating spiral pattern appeared in a non-locally coupled oscillator medium, then this pattern would necessarily include a local group of incoherent oscillators other than a coherent group. The reason is this. Unlike the case of locally coupled oscillators, the oscillators sitting at the center of rotation need not have vanishing amplitude. What must vanish there is a local order parameter. Then the local order parameter in some region around the center of rotation will have small amplitude, and that will too weak to entrain the oscillators distributed there, whereas where apart from the center of rotation, the local order parameter will be large enough to entrain. Consequently, the pattern will split into two regions, that is, incoherent inner region and coherent outer region. This type of chimera was actually confirmed by numerical simulation for the Fitch-Nagumo oscillators and also phase oscillators, each with non-local coupling. The corresponding mean field theory was also formulated. This work was done by Shima and myself in 2004. Chimeral states were also realized in experiments, although outside of experimental settings, their existence in the real world is still controversial. Theoretically, Many variants of chimeral states were proposed in different connection topology. We now realize that pattern of synchronization of coupled oscillators can be far more complex than we expected decades ago. In concluding this talk, I'd like to make a remark on dynamical reduction, such as the center manifold reduction and phase reduction. I think that dynamical reduction is significant in two respects. First, as anyone may agree, it cuts off many details which seem inessential for qualitative understanding of the system under study, thus making the analysis far easier. It may also happen that reduction can uncover novel dynamics that was not anticipated. For example, one example is the discovery of turbulent behavior of the brassulator, which would have been very difficult without its reduction to CGL. The second point of significance of dynamical reduction is, in some sense, more conceptual than practical. We are more concerned with a broad class of systems rather than individual specific systems. By this I mean that reduction reveals something universal lurking behind apparently different systems and situations. Regarding the phase oscillator model I proposed years ago, it may have served as a small piece of such universality. It's an extremely boiled down model as an inevitable result of double reductions, and therefore it could only capture the crudest level of universality. Still, for its extreme simplicity, it leaves much room for generalization in various ways, and in fact this has been done over the past half century. Consequently, a broad class of oscillators models have been created, and they will be of great help for further understanding and controlling what is going on in the real world. With a hope for further advancement in the field of oscillatory dynamics and synchronization, I'd like to conclude my presentation. Thank you for your attention.